Welcome back to ECE 442-542. Homework number 3 is due Monday on the 25th. There are some hints for problem number 4 on that in D2L, and exam number 2, I wanted to say exam number 3. You would have thought you missed an exam, but exam number 2 is scheduled for after spring break, March 13th. And there are some additional notes, no video, thankfully for you, right? There are notes, handwritten notes on how to inversely transform rational expressions that might possess complex poles. And we haven't really talked about that in class, but those notes should provide you with a couple of different ways of doing that, either keeping with real coefficients in the denominator with those complex poles, or actually factoring those quadratics into a complex conjugate set of pairs and finding the partial fraction expansion coefficient from those transformed or those partial fraction expressions. What I want to do today is try to give you just a little bit of material so that you will be able to quickly work one of the other homework problems if you haven't already, which is to inversely transform by long division. And that might be useful if you simply want to check the first 2 or 3 sequence values in a time domain sequence without having to go through the formal process of inversely transforming the expression. You can now just do a few long division operations and find those sequence values at the beginning of the sequence. Then we'll play a matching game. Oh, maybe that's the wrong word to be using, match and game, but anyway, we'll play a game that involves matching different sets of information. You won't slide right, you won't slide left. Is that what you do with match? I don't know what you do with match, but I've heard rumors. We'll have some fun with region of convergence. Then we will summarize those. You'll be getting bored with this probably, but hopefully it will all be making sense to you. We'll talk about system stability and poles inside the unit circle. We'll look at some examples of what it means relative to a system being causal or non-causal, and does that mean that it has to have a bounded time sequence or an unbounded, and we'll show that those two properties, causality and boundedness, are not connected. They're independent properties, so don't get them confused saying, oh, that's a causal system or a causal signal, it must have a bounded response. That's not necessarily true, or just the opposite. It's anti-causal. It can also have a bounded response sequence associated with it, or an unbounded. We probably won't get there, but if we do, we'll start talking about the next topic, which is discrete equivalence. How do you find a transform expression in the z-plane from a transform expression in the Laplace domain, in the S domain? How do you go from g of s to g of z? And there's many different reasons for performing discrete equivalence, and we'll have to become comfortable with understanding when do you want to use which particular strategy to find a discrete equivalent. To do the long division, or to find the sequence values by long division, we're really playing on the fact of this series expansion of a transform, capital X of z. It now looks like a sum of terms involving powers of z to the minus 1. And what the coefficient is associated with each of those powers will actually give you one of the terms in your sequence of numbers, x at minus 2, x at minus 1, x of 0, etc. For this example, we're going to focus on the causal time sequence. We're not going to worry about the sequence values that have negative time indices. And if you were concerned with something that was not causal, you would have to do a modification of this strategy, and that's really what I'm trying to say here. But before I even give you time to read that, let's look at the example, and you can look at that later as a exercise of accessing the material on D2L. So let's now look at finding little x of n, or a few values of little x of n, from this transform expression. And because of the region of convergence, the magnitude of z being beyond a given value, which in this case is beyond the largest pole in the denominator expression, or in x of z, we know it's causal. We know the time sequence associated with capital X of z is a causal waveform, and now what we want to do is really just perform long division to generate those values of the time sequence. To do that, it might be helpful to actually find or multiply these numerator and denominator factored forms out. If we now multiply the numerator, we have 4z squared plus 4z, and downstairs we have the quadratic z squared minus, I'll just write it as 2.5z plus 1. We can now use whatever way you learned how to divide polynomials, wherever you learned how to do that. Let me just write it down as a long division problem. And now we have the numerator under the division symbol, and we have the denominator dividing into it, which is z squared minus 2.5z plus 1. We now perform the division. What do we need to multiply that denominator, z squared minus 2.5z plus 1, to give us 4z squared? Or divide 4z squared by z squared. We just need a number of 4. And now we multiply the denominator by 4 and subtract that from what we started with in our numerator. Or we now have 4z squared. We have 4 2.5s, or 2.5 I think of a quarter. 4 quarters are $1, so we're up to 10. We now have minus 10z, and 4 times 1 is simply 4. Subtracting that line from the numerator expression, we now end up with the z squared term going away. We subtract a minus 10, and we now end up with 14z minus 4. We now say, what's it going to take to multiply something by z squared to end up with 14z? And now it's going to be that 14z to the minus 1. So that now this becomes 14z, and now 2.5 times 14, or 28 plus 7, 35, with a negative sign, minus, what did I just say, 35, and then plus 14z to the minus 1. We'll do one more. We subtract that and we get rid of the linear power of z. We subtract or add 35 to minus 4, and we have 31 minus 14z inverse, and now we can say, oh, up here we need plus 31 z to the minus 2. And we could keep going, but this is all the further I want to go. What we're doing now is comparing this expression with that series expansion. What is scaling by z to the 0? That will be our x of 0 coefficient. Here is now x of times 0. This coefficient, which is scaling z to the minus 1, is now x at 1, and here is our coefficient at time 2, or x at time 2. And that's a way to find a few of the sequence terms without doing the inverse Z transform, and you could maybe check your work if you wanted to doing this and saying, okay, do these sequence values actually align, or are they equal to what I would obtain if I evaluated my expression for little x of n that I've generated using the inverse Z transform? And I think I asked in one of your homework problems to do some long division. That's all I'm asking you to do, is remind yourself how to perform long division, but that's now useful as a strategy or as a tool to find these sequence values independently of doing the inverse Z transform. What questions do you have after that discussion? Everyone's on board with performing long division? You thought you were never going to do that again, right? After you finished 3rd grade or whatever grade you were in when you were doing long division. Well, if you missed that opportunity, now it's back. Let's now go into our matching game. And I really want to play this because of the pictures that I've drawn. I hope you appreciate the figure that's in the lower left. Kind of looks like an eyeball staring at us. Maybe it's a little bit weird, but so be it. We now have 3 poles and 3 different possible region of convergences. We have the green region of convergence, which I'm labeling A. We have the blue, and these are supposed to be concentric circles. We have the blue, and the blue is now lower bounded by 1/2 and upper bounded by 1.5 by the poles. And then we have the gray shaded, or the black region of convergence, which is lower bounded by 2. We have 3 region of convergences, and now what I want you to perform is the matching of the region of convergence with one or the other or all of the support intervals. The support intervals are in the time domain. 1 is n greater than or equal to 0, or a causal sequence. 2, a two-sided sequence, and 3 is an anti-causal. Meaning, which region of convergence or convergences correspond to 1, 2, and 3. I want you now to write down A, B, and C, and next to those write down 1, 2, or 3, and it doesn't necessarily have to be a one-to-one mapping. Maybe it's one-to-many. Are there different regions of convergences that correspond to the same numerical value or not? But I hope it's clear what I'm wanting you to do. I want you now to determine, based on these region of convergences, which support interval or interval of support goes with which region of convergence. Everybody have an answer? Should have 3 different numbers or 3 different possible numbers associated with the 3 different region of convergences. I'm going to have you now indicate. Why don't we use 1 as a thumbs up, 2 as a level thumb, and 3 as a thumbs down. 1, 2, 3. I don't know if I can see your fingers. I don't have my glasses on, but maybe I can. I guess maybe I can be very liberal with my counting. So we can say 1 finger, 2 finger, or 3 fingers being held up for the different region of convergences. Are we ready to respond? At the count of 3, region of convergence A corresponds to 1, 2, or 3. At the count of 3, show me your finger. Fingers. Yeah, and anyway. So we'll do 1, 2, and 3 in that order with your fingers. 1, 2, 3. So am I seeing 3 mostly? So you're saying that region of convergence A, well, let's just do them all and then we'll talk about them. B. At the count of 3, give me your fingers for B. 1, 2, 3. All right, we're seeming to get all of this, maybe. 2, and now we're going to blast off. What's C? 1, 2, 3. That was maybe 2 canned. So it should be 3, 2, 1, and I think you now understand, obviously, the connection between region of convergence and causal, anti-causal, and two-sided. The annular region, which is region of convergence B, is two-sided. When the region of convergence is interior to all of the poles, it's anti-causal, and when the region of convergence is beyond or exterior to all the poles, it's causal. Those are the correct answers. Let's try another one. Here I want to ask you the following. For these different region of convergences, how does the signal behave? Is the signal's behavior corresponding to bounded with exponential decay? Is it bounded no decay? Or is it unbounded with exponential growth? Those are the 1, 2, 3s. So now write down for A, B, C your answer, whether it's number 1, number 2, or number 3 for the different region of convergences. And now you need to pay attention to where the poles are relative to those region of convergences. Everybody have an answer? All right, for region of convergence A, guess I need to, no, I'll just keep my pen. Let me do black. So for region of convergence A, count of 3, 1, 2, 3. I see a few 1s, mostly 3s. Talk to your friends and figure out which one it is. Is it 1 or is it 3? If you're playing along at home, try to convince yourself by an argument why you just said the answer that you did. What's your argument if you chose number 3? How did you argue if you selected number 3? How do you justify that there's an unbounded response with exponential growth? Pardon? The region of convergence doesn't include the unit circle, which is a valid reason. Can you show me or explain now which mode might be unbounded, or are they all 3 unbounded modes? What's giving rise to the unbounded behavior? If I said, okay, here's x sub 1 of n, and maybe I just pick 1 or 2, if they're all 3 unbounded, just give me one of those 3. Which of those, any of those modes, what are your modes? You have 1/2 to the n, you have 1.5 to the n, and you have 2 to the n, right? Those are your modes. And now I'm hearing somebody say the 1/2 to the n. And why did you pick 1/2 to the n? This is for an anti-causal waveform, isn't it? From part A of this quiz, this region of convergence corresponds to little n's that are negative. And now if we raise 1/2 to larger and larger negative powers, that's going to go unbounded. So there is the justification for why item 3 is the answer, the correct answer. What about B? So this is just one of the modes. Not all 3 actually go unstable. How many does it take? How many modes does it take for an unbounded response? Just 1. And there's the 1. The other 2 are well behaved, in fact. They do decrease or decay. Region of convergence B. 1, 2, 3. I see some 1s, I see some 2s. Which is it? 1 or 2? Did I see any 3? So everybody thinks it's bounded or bounded so bounded no decay or bounded exponential decay. So which one is it? 1 or 2? What's it mean for bounded no decay? That would be like a constant response, correct? With time, with n. Is the response associated with region of convergence B performing that way? What are our modes? We have 3 modes, correct? are all of these modes valid for the same range or interval of support for little n? Do these all correspond to the same range of n values, these modes, relative to region of convergence B? This is now the annular region, and so now we have some poles that are outside or exterior and some that are interior to the region of convergence. What happens to the modes that are interior to the region of convergence? Do they correspond to non-causal or causal values of n? Positive values of n or negative values of n? And I'm in particular asking this 1/2. That pole is now bounding the region of convergence on the interior of that region of convergence. Does that now correspond to negative n's or positive n's? What did it do in A? Does that make... It was for negative. Isn't it negative still? No, because it's on the other side of the region of convergence. In this particular region of convergence, this 1/2 to the n is actually for non-negative values of n. And what happens to 1/2 when you raise it to higher and higher powers of positive n? That exponentially decays. What about the other two? Those two now live outside or exterior to the region of convergence. Those now are consistent with what we had interval of support-wise for part A. These are now exterior. These are now associated with negative indices. And what do we have for those? Now we have something bigger than 1 raised to higher and higher negative powers, and those are collapsing. Pictorially then, we have something that if you wanted to just roughly sketch, is doing something like that on either side of n equals 0. They're exponentially decaying on both sides of n equals 0. This one then should be giving us bounded behavior, and it's actually exponential. So the answer should be number 1. So that was bounded with exponential decay. What about region of convergence C? And I'll count to 3 for region of convergence C. 1, 2, 3. See mostly 3s. I see a few 1s. Is it exponentially decaying? And if it is not, what's causing it to not be exponentially decaying? Your modes are the same. What's the interval of support? When is this valid? For this particular piece, we have x of n is again, let's say alpha 1 bar 1/2 to the n plus alpha 2 bar 3/2 to the n plus alpha 3 bar 2 to the n. And when is this true? Are they all for the same n values? And if they are, what are the n values that they're valid for? This now corresponds to a causal sequence because your region of convergence is beyond all of the poles. Do any of those give you trouble relative to bounded behavior. Yeah, there's a couple that are outside the unit circle. So if you wanted to, you could have argued for this unit circle argument again. The unit circle is not included in the region of convergence. These two modes actually are unbounded, and for that reason, answer 3 is the correct answer for this. So 3 answered 2 of the questions, and 1 answered the middle one. Now I might ask you the following. What would poles look like, or where would poles be located if I had bounded behavior with no decay? Can you sketch pole locations that would correspond to bounded behavior with no decay for any particular interval of support? Unit circle. So you want a pole on the unit circle? Poles not on the unit circle? What am I doing with the unit circle? I didn't bring scissors, so I can't cut it out. I'm being kind of difficult here. Where do we want our poles relative to the unit circle? Right around it? What do you mean by right around it? So now we actually want these poles. What if I put a pole right there at 1? So now this particular pole, if this was the only mode, if this was a system and it had a pole at 1 and you walked up and kicked it, it would just give you a constant value out. It wouldn't exponentially decay because the mode for this is 1. 1 raised to the n, 1 raised to the squared, 1 cubed, 1 to the 4th. It's always 1. So whatever you kicked it to, it would stay at that value. What if I gave you poles there? Would that give you bounded no decay? What does that produce? Poles at those 2 locations, where maybe I throw out the pole at 1. Pardon? This now gives you oscillation with a frequency determined by the angle of those poles. So this you can think of as a cosine or a sine wave at a particular frequency. And the speed or the number of points you see in that oscillation is determined by the angle that that pole makes with the right hand or the real axis. And so I could now put poles anywhere on the unit circle, and those will give me a bounded response with no decay. But if I now had a system that had a pole, any of those pole patterns on the unit circle, would it be a bounded input, bounded output stable system? Now I'm asking, if I gave you a pole at z equal to 1, could I find a bounded input that would cause an unbounded response? I've changed up the problem a little bit, but here bounded no decay, maybe I should just say, corresponds to poles on the unit circle. Now I'm changing it a little bit, and I'm saying, what if we had g of z that looked like that? Maybe we could even put a 0 there if we wanted to. And now we put in an input, r of z, that was also right there. So that now here's g, here's r, and here's y. Is y bounded? Or really, is the time sequence y of n bounded? I hope that's sort of clear. Is y of z bounded in the inverse Z transform? Do you remember what the inverse Laplace transform of 1 over s is? Hopefully that didn't mess everything up. Is y of n bounded? It's not. So you could actually find a bounded input, r, applied to a system that has a pole on the unit circle whose output will go unstable. Meaning, now if you had poles, let's say, that are in the first and fourth quadrant, and if you put in a cosine at that same frequency or a sine at that same frequency, you're now exciting the system at its natural mode, and you're going to get an unbounded response as well. You could put in a bounded input and generate an unbounded output. Meaning, poles on the unit circle are not really what we want if those are corresponding to a system, because they don't represent a bounded input, bounded output system. Bounded input, bounded output stable system. We could find a bounded input that would cause the system output to go unbounded. Do we require all of the poles? Here's another variation on that. Is it necessary for all of the poles to be on the unit circle to produce a bounded response? What would happen if I had poles like that, where this is now the unit circle, and let's assume that here is the region of convergence outside of those unit circle poles? Would that produce a bounded response, or would it produce a decaying response? And if you don't like all three poles on the unit circle, just put the pole at z equal to 1 and everything else inside the unit circle. Will that give you a bounded, no decaying response with an initial condition response? I'm not allowing for a constant input because we know it would go unbounded. Do the exponentially decaying poles cause everything to go with a decay? Or what's the answer to all poles on the unit circle for a bounded response? Yes or no? Yes, thumbs up. No, thumbs down. We ready to answer? 1, 2, 3. So I see some ups, I see some downs. I forgot what I asked for up and down. I see some sideways. Up means, what did I say up meant? That yes, you have to have all poles on the unit circle for a bounded response. The answer is actually no. You can have poles inside the unit circle, one pole on the unit circle or a pair on the unit circle, and you'll have a bounded response even if you have 10 or 20 poles that are inside the unit circle. So all poles on the unit circle are not needed for a bounded response. The answer is no. I'm not sure which thumb position that corresponds to. I think down. So all poles on the unit circle for a bounded response, no. We getting comfortable with all of these possible intervals of support, bounded behavior, region of convergences? How can we summarize? Pattern number 1, what was that? That was where we had our region of convergence, and now this circle is just the boundary of the region of convergence. It's not associated with the unit circle. Pattern 1 corresponds to what interval of support? Two-sided, one-sided, and if it's one-sided, is it in non-negative or is it in negative for this pattern? You just told me you knew all of these region of convergences. Is this two-sided? It's not a donut, is it? It's one-sided. Is it causal or non-causal? Causal. So this one now corresponds to a causal. And this is when Z is bigger than A. What's the modification to this? How do we modify this one to make it more general than causal? Instead, it's now right-sided, meaning we could actually have a few sequence terms with negative values of little n. That's what we're calling right-sided. Now we have right-sided with the modification. And for this, I'm saying that x of n is equal to 0 for n less than m, and m can be negative. How do we modify this region of convergence? Do you remember? What's the modification? We eliminate one of the extreme points, don't we? And that extreme point is infinity. So the modification is now Z is magnitude bigger than A, but now it's bounded. It doesn't include infinity. That's the modification that allows us now to have a few sequence terms, a finite number, that have negative indices. What about pattern 2? This one's non-causal. And what if we modify it? the modification makes the time domain sequence left-sided, and that's when we don't include the origin in that region of convergence. So we've now removed that z equal to 0. And here, x of n is equal to 0 when, let's say, little n is bigger than capital N, and big N can be positive. Finally, pattern 3 is our two-sided, and what's the modification here? Or what does, before we get there, what's x of n look like here? Alpha 1 a to the n and alpha 2 b to the n. What are my intervals for n on the first row for a, for that mode? What does it correspond to? N less than 0 or n greater than or equal to 0? That's the causal piece. The anti-causal piece is for B. Is there a modification to this pattern? No, it doesn't include the origin, and it doesn't include infinity with this annular region. What about this pattern? The inverse donut. Is that a region of convergence? Yes or no? Why is it not a region of convergence? The region of convergence needs to be connected, meaning you need to be able to, if I had a point here, let's say at point A, and I had another point in the region of convergence B, I need to be able to connect those 2 points by staying in the region of convergence. In this case, I can't get from A to B without leaving the region of convergence and going through that unshaded region. The region of convergence needs to be connected. So this is not a valid region of convergence pattern. Let's now talk about system stability. I've been talking about that already, but let's tighten that discussion up just a little bit. And I'm going to say this discussion is associated with this controls class. The key word there is controls. It's not a signal processing class. And in this controls class, for stability, we want poles inside the unit circle in order to maintain or to have stability. And I think the earlier discussion hopefully convinced you that you can't have poles on the unit circle, because you could now find a bounded input that would cause the output to go unbounded. And we want bounded input, bounded output stable systems. We want then for this controls class our poles to be inside the unit circle for stability. Now we could look at that from a signal systems perspective. Let's say here's our system. And the reason why I'm saying in this class and inside the unit circle, we had bounded responses for poles outside the unit circle. So what's the deal? Well, those were corresponding to anti-causal waveforms. Our systems now, we're going to assume are causal. Here's, let's say, the input, R of n. Here's the output, Y of n. This is our excitation, or the input waveform. Here is the response, Y of n, due to exciting the system with this signal, R of n. Now, what's it mean for a system to be causal? So now if a system is causal, that basically means that it can't respond to a signal before the signal occurs. It has to respond to the signal after the signal is applied to the system. You can't be shaking, the system can't be shaking and then you hit it. That would be non-causal. So a causal system means you hit it and then it starts moving. There may be some delay between when you excite it and when it starts shaking, but it better not be shaking before you even hit it. So that's what we mean by causal. The response actually occurs after the excitation. That's the causal. So that means then that the impulse response associated with that system is associated with indices n greater than or equal to 0. Or our picture now produces the following. If we have a causal set of poles, and let's say our poles are here, here, here. Oh, and these should be conjugate pairs. So if they're off the real axis, they need to be a mirror image above and below. So we're assuming that these are now complex conjugate poles. If these poles correspond to a causal waveform, which our system now is said to behave like, what's the region of convergence? Where is it relative to these poles? Based on what we've talked about. How would you draw the region of convergence for this set of poles in the z-plane? Would I find the poles closest to the origin and find the inner circle and shade that? Not based on what you've been telling me so far today. We would actually find the pole furthest away from the origin, draw a circle enclosing that, and let's say that's now a distance r, which means then for a causal behavior we need the region of convergence to be outside of that radius. And to be stable, where do we need our unit circle? So here's our region of convergence. Now to be stable, we need all of those poles. That's supposed to be the unit circle. To have values, because now those modes are going to be raised to ends that are non-negative, and that means they have to have magnitude less than 1. And this is the picture now that is associated with a system in this class that's going to be stable. We need all of its poles inside the unit circle. That's why if we now start talking about stability, you say, oh, where are my poles relative to the unit circle? That's why we're making that connection. Observation. The causal nature of our signal, or signal causality, whether it's causal or non-causal or anti-causal, and whether the signal is bounded. So now signal causality and bounded time response of that signal, or time response behavior, are two actually separate characteristics. Meaning, a signal can be causal which means that signal is defined for n greater than or equal to 0. And where's the region of convergence for a causal signal relative to the poles? The region of convergence is interior to all poles or exterior to all poles. If we have a causal, it's now exterior. So a signal can be causal, meaning it's defined for n greater than or equal to 0. The region of convergence is exterior to all poles, yet this signal could be unbounded. If that's the case, where are the poles, where are the modes, if we have an unbounded response for a causal waveform? Those poles need to be outside the unit circle. For example, here's, and now if it's not clear, I would just start putting together some example waveforms. Suppose I now give you that, h sub 1 of n. Let's say this is example 1. It's causal. N is greater than or equal to 0. What's the picture look like if we now looked at the pole 0 pattern relative to the region of convergence for this particular combination? The pole is located where? At z. This is the z-plane. Where is the pole in the z-plane? It's at 5. Where's the region of convergence? It's now outside of that pole. The poles can't be in the region of convergence. And there is a causal waveform that's unbounded. That pole doesn't have to be inside the unit circle to be causal. What about the opposite of that? Example 2. A signal can be non-causal defined for n less than 0. The region of convergence here is now interior to all poles. And we can still have an unbounded response. Where are the poles now to produce? Are the poles exterior to z equal 1 or interior for a non-causal signal? These are now interior or inside z equal to 1. An example might be h sub 2 of n equaling 3/4 to the n for n less than 0. The pole is at 3/4. Our region of convergence, because it's non-causal, is interior to that. And this is the z-plane. What's the time response look like? At -1, it's 3/4 to the -1. We just invert 3/4, it's 4/3. What is it at -2? 16/9. Not quite 2. It was a little bit more than 1 before. Now it's not quite 2. What is it at -3? 4 cubed, 64, over 3 cubed, 27. That's bigger than 2, isn't it? So now we have, and that just keeps going. So we do have an unbounded, non-causal waveform. What are the other two cases? Can you come up with an example that's a causal sequence that's bounded? And you hope that I give you that on the next exam, right? What's h sub 3 of n? What's one possibility? When is this defined? This is defined for n greater than or equal to 0. The mode now is something. What's that mode? Just needs to be less than 1, doesn't it? So 1/4 to the n would be sufficient. If we drew this z-plane plot of pole and region of convergence, we would be at 1/4. Our region of convergence is beyond that lower value, and the unit circle is included in the region of convergence. So we've done a causal unbounded, a causal bounded, a non-causal unbounded. Now we just need to come up with the last one, example 4, which is a non-causal sequence that is bounded. What needs to be inside the brackets? Just anything bigger than 1. And you could hit it hard if you wanted to and pick a 6. So that now we have, for the picture, now we have a pole at 6. Our region of convergence is now bounded on the exterior by that region of convergence, and now we've illustrated all the different possibilities for causality and bounded behavior. If I now give you the task of finding an inverse Z transform. So to find a unique inverse a unique little x of n, what do we need? How many things do we need? What if I give you capital X of Z? Can you give me a unique x of n? Can you now find little x of n, a unique little x of n with that piece of information? Do I need to tell you anything more? You have to be told the region of convergence in order to get a unique answer. So, and we need 2, the region of convergence. As an example, suppose we now have capital X of Z is Z over Z minus 1/4 and Z minus 2. And let's say the region of convergence is now annular. What are some questions that we might want to keep in mind as we're now trying to determine little x of n, given these 2 pieces of information? First thing you might be thinking is, where are my poles, or what are the modes that I'm going to see in a little x of n? Where are the poles? And that's easy to find based on this factored form of the denominator. I could have given you the denominator in a quadratic. You would then need to find the roots of that quadratic. Here that's not hard. That's already factored. We know our modes are going to be at 1/4 and 2. That's one question that we can quickly resolve. A second question might be, is x of n one-sided or two-sided? What's the answer there? It's two-sided since we have an annular region of convergence. What's the structure of x of n? We have a mode at one pole, and we have another pole or mode at the other pole. And when are these two different poles, are they valid for the same interval of support on n? Where is this pole relative to the unit or to the region of convergence? Is it interior or exterior? Is it on the inside of the donut or the outside? So this one now is, what's the structure? So here's my region of convergence. And you could quickly draw that. And 1/4 is now on the inside of that donut. 2 is on the outside. If that's the case, then what values of n, or this is now a pole that's interior to the region of convergence, or the region of convergence lives outside of it, what are the values of n that this now is true for? N less than 0 or greater than or equal to 0? And likewise for this, this is because the pole here is exterior. Is x of n a bounded sequence? Yes, because now for those ranges on n, for each of those modes, they're going to be decayed. And you could also say that it's bounded for the other reason, which is the region of convergence includes the unit circle. So now how do we find the inverse Z transform? We have one transform, but we have basically these modes corresponding to two different intervals of support. Can we do the partial fraction expansion? So the key here is, yes, we can do the partial fraction expansion. It's just now how do you go from those partial fraction terms back into the time domain depends on whether it's a causal sequence or a non-causal sequence. If it's causal, then the sign, SIGN, between the frequency domain and the time domain remains the same. If it's non-causal, there's going to be a sign inversion between the time domain and the frequency domain. I'm telling you that because I can see that I'm running out of time, but now what I want you to look for after the fact is the notes that I'll try to put together that show, okay, we can do the partial fraction expansion. Now, how do we take that transform expression into the time domain? Well, it depends on whether that particular transform expression corresponds to a causal or a non-causal time domain waveform. If it's causal, then we don't need to change the sign of whatever that partial fraction coefficient was in our expansion. Let's say it was 7. It would be 7 times 1/4 to the n. The other piece, if the partial fraction expansion was 6, then we would say, oh, it's minus 6 times whatever that was, 2 to the n, for n less than 0. So we have a sign inversion when we have anti-causal. We have a sign preserved in the causal. I'll let you look at what I try to write down after class to make that clear. But hopefully that will be clear.